Hi guys, welcome to this video where we're going to take a look at another problem from the book that I've used in some of my previous videos, or that I've referenced in previous videos, Challenging Problems in Algebra by Alfred, Posamentier and Charles Salkind. So this problem is from chapter 5 in this book, and it's problem number 18. And I thought this was an interesting problem, quite a unique problem, one that I've never seen anything like it before. So the problem is, find the two prime factors of the number 25,199 if one factor is about twice the other. There is a challenge problem as well, a follow-up challenge problem, which I'll get to after we've had a look at this problem. So the number that we're interested in is 25,199. So we're told that evidently 25,199 can be split into a product of two prime factors. So there's a few things that we're going to need to be aware of here, that we're going to be conscious of as we work through this problem. So one is that if we split a number into its prime factorization, or decompose a number into its prime factorization, that prime factorization is unique. Unique at least up to reordering of the numbers. So for example, if we take the number 18, 18 as a product of prime factors is going to be 2 times 3 times 3. Now obviously we could write this as 3 times 2 times 3, but all this hasn't changed the factors, it's just changed the order that we're multiplying the factors. So these would be considered one and the same thing, effectively. They're both the same prime factor decomposition of the number 18. And there's no other prime factor decomposition that we can find for the number 18. And that applies to any number. And this is called the fundamental theorem of arithmetic, that any number greater than or equal to 2 is decomposable into a unique product of prime factors, or decomposable into a product of prime factors in a unique way. Something else that we're also going to need to pay attention to as we solve this problem, or something that I thought was useful to bear in mind, is that when we multiply two numbers together, doesn't matter which numbers they are. So let's say we've got 367 times 4,189, for example. Let's say I want to know what is the terminal digit of the product of these two numbers. So 367 times 4,189, the terminal digit of the product of these is going to be 3. How do I know? Because 7 times 9 is 63. In other words, the product, if I just look at the product of the terminal digits of the two individual numbers, 7 times 9, which is 63, 3 is the terminal digit of that product, and therefore must be the terminal digit of the product of 367 and 4,189. So these are going to be some useful things that we're going to need to pay attention to as we work through this problem. Okay, so we're also told that the prime factors, x and y, so we've got x times y equals 25,199. We're told that y, let's take x as the smaller of the two prime factors. Y is approximately equal to 2x. So notice it's approximately equal to, not exactly equal to. So we've got to be aware of that. So the way that I started this problem was to think, okay, rather than multiplying x and y to give 25,199, then if I multiply x and 2x to get 2x squared, this will be approximately equal to 25,199. So it might be a bit more, it might be a bit less. So approximately equal to is often, we often use kind of a wavy equal sign to indicate approximately equal to. So that means that x squared is going to be approximately equal to, let's say, 12,500, 12,600-ish. Okay. So what I need to do now is I need to start hunting for numbers x whose square is going to be about 12,600. And I don't necessarily need to be too exact about this, but what might be a good idea is for me to try to establish some kind of bounds. So for example, I know that if x is equal to 100, then x squared is going to be equal to 10,000. So that's going to be too small. X equals 100 is going to be too small. Whereas if I go right up to say 120, x squared is going to be equal to 14,400. So that's a bit too big. So I know that x, the actual value of x that I'm going to be looking for is going to be somewhere between 100 and 120. So let's just go halfway. X equals 110. So if x is equal to 110, then x squared is equal to 12,100. Oh, that's very close. That's really close to 12,600. But let's just go a little bit higher. Let's go to x equals 111 just to see what happens. So in that case, x squared is going to be equal to 110 plus 1 squared, which is 12100 plus 220 plus 1, which is 12,321, if I'm not mistaken. Which is, okay, it's still a bit kind of short of 12,600. So let's just go for x equals 112 just to see what happens. So x squared is going to be equal to 110 plus 2 squared, which is 12,100 plus 440 plus 4, which is 12,544. That's not too bad. So x equals 112 seems to be a good number. It's a number that when I square it, it brings me to something that's close to 12,600. Remember, we're not looking for exactly 12,600, just something that's close enough to it. So 12,544 seems close enough. The problem is x equals 112 is not a prime number, unfortunately. Okay, so what I need to think about then is what are possible prime numbers around the value of 112. So let's try maybe x equals, I don't know, 113 maybe. I don't actually know if some of these are going to be prime numbers. 115 is definitely not going to be a prime number. 111 I think will be too small. I don't actually know if 111 off the top of my head. I can't think if it's a prime number. Maybe it is, maybe it isn't. We'll find out in a second. Okay, so I don't think it's going to be 111. So I'm tempted to go for 113. Why do I think that? I don't know. I just don't think it's going to be 111 for some reason. So, okay, what about the value of y? Well, twice x is 226. Again, 226, not a prime number. Okay, but remember that y only has to be approximately twice x. So we need y to be around 226. And now here we kind of turn our attention to the fact that the terminal digit of our product, x times y, must be 9. So that means that if x is equal to 113, y is going to have to end in a 3. So that gives me maybe two possibilities, 223 or 233. I think 233 is a bit too high, so I'm going to go for 223. So I'm going to go for these two numbers. Now, I don't know whether these are the two numbers that I need. The only way for me to find out is to actually try them, to see what happens when I multiply 113 by 223. So let's find out. Let me clear some space here. So 113 times 223. So this is going to be equal to 110 plus 3 times 2 times 110 plus 3, which is twice 120, 12,100 plus 6, 9, 190 plus 9. So that's going to be 24,200 plus 999. No, that's nice and easy. So that's 25,199. So remember what I said right at the beginning. Once we've split 25,199 into two prime factors, then it's unique. There's no other possibilities. So what I found here is that 25,199 can be split into decomposed into the products of 113 and 223. These must be the prime numbers that I'm looking for. Okay, so let's have a look at the follow-up challenge part to this problem. And by the way, this is a new YouTube channel, a fairly new YouTube channel, very small at the time of recording this video. I've only got a few subscribers, so I'd really appreciate it if you like this video, give it a thumbs up, and it would be great if you could subscribe to this channel and let other people know about it as well. So let's have a look at the next part of this problem. It's very similar in many respects, but this time we've got find the three prime factors of 27,931. So 27,931 if the three factors are approximately, again approximately, in the ratio 1 to 2 to 3. So in other words, we've got three prime factors, x, y, z, where, again, let's take x as being the smallest, the smallest value. Then y is going to be approximately equal to 2x, and z is going to be approximately equal to 3x. And I'm going to use a similar technique to what I used for the previous part, but there's going to be a little bit more work for me to do with this particular problem. So rather than multiplying x, y, z, I'm going to think, what do I get when I multiply x by 2x and 3x? I'll get 6x cubed, and this is going to be approximately equal to 27,931. Again, we're using this symbol approximately equal to. It's not exact. A lot of this is based on a bit of trial and error, and it's based a lot on gut feeling and instinct. So understands that when you're solving a problem in mathematics, the final solution that you give, that you present, has to be logically consistent. It's got to be logically valid. But the way that you actually come up with the solution itself might be very different. And sometimes it will be based on gut feeling. And you may have ideas sometimes, and you don't necessarily know what motivates the idea, but you know that you need to go with that idea. It's not necessarily motivated by some cold, hard logic or anything like that. And it's important for you to learn to listen to that. When your brain, when your mind is telling you, is giving you ideas, you've got to learn to listen to that and follow through with some of those ideas. So 6x cubed is approximately equal to 27,931. So that means that x cubed is going to be approximately equal to, what's this, divided by 6? Well, 6 times 4,000 is 24,000, and 6 times 5,000 is 30,000. So we're looking for somewhere in between those two, in between 24,000 and between 4,000 and 5,000. I'd say it's going to be about 4,500. So x cubed is going to be somewhere between, I would say, 4,500 and 5,000. Somewhere in there. Again, we don't need to be exact about this. So, okay. Again, I'm going to try to get some bounds on this. So maybe if x is equal to 10, then x cubed is naturally going to be equal to 1,000. That's far too small. If x is equal to 20, x cubed is going to be equal to 8,000. That's too big. So the number that I'm looking for x is probably going to be somewhere between 10 and 20. Okay, so x equals 15. 15 is not a prime number. So I reckon x equals 13 or x equals 17 are going to be the sensible possibilities here. X equals 13, that I think is going to be too close. That's going to be too far. It's going to be closer to 1,000 than 8,000. I need something that's between 4,500 and 5,000. That's a bit closer to 8,000. So I'm going to go for 17. X equals 17. That seems like a sensible one for me to go for. So what is 17 cubed? Well, 17 squared is, well, I don't know off the top of my head. 10 plus 5. 17 squared. 10 plus 7 squared, 100 plus 140 plus 49. 289, of course, yeah. And 289 times 17, oh, goodness. 289, so it's going to be 2,890 plus half that, 1,445 plus twice this. I'm going to round this up to 300. Remember, we're interested in approximations here, so let's just call this 300. So it's going to be approximately equal to 2,890 plus 1,445 plus, let's say, 600. So what's that equal to? 2,000, 3,000, 3,000. It's going to be 4,200, 4,800. Right, yeah, so it's going to be about 4,800-ish. So this seems to be in the right sort of place. Again, I don't need to do exact calculations here. And the reason that I'm not reaching for my calculator is because I don't need it. I don't need to do exact calculations right at this moment in time. I just need to find a number whose cube is somewhere between 4,500 and 5,000. 4,800-ish, that's perfect. That will do. So I reckon the value of x is probably going to be 17 in that case. I don't know for certain. It could be 19. I think 19 would be too big. So I'm going to go with 17. So now, again, we've got to think, what are the possible values of y and the possible values of z? So if x is equal to 17, y is approximately twice this. So y is going to be a prime number around the value of 34. So y could be equal to maybe 31 or 37. Possibly, oh no, 39 is not a prime number. So 31 or 37. And then z, which is 3 times this number. 3 times 17 is 51. So prime numbers around 51, maybe 53. Any others? I think 47 would be would be too small. Let's include it though. 47, I think it's a prime number. 53, 55 is not a prime number. 57 is not prime. 59, I think is going to be too big. So let's leave it at that then. So now, again, we need to consider the terminal digit of this number. It's 1. So that means that the three numbers x, y, z that I choose have to, their terminal digits of each of these numbers has to, the product of their terminal digits has to also end in a 1. So for example, if I choose x equals 17, y equals 37, and z equals 47, for example, the terminal digit of x, y, z will be 7 times 7 times 7, which is going to be 3. 7 times 7 is 49, times 7 again is 243. So that combination is out. That doesn't work. Similarly, if I chose the combination x equals 17, y equals 31, and z equals 47, the terminal digit of that product is going to be 9. That conflicts with what we've got here. So I'm going to stick with x equals 17. So then I've got to think, if y is equal to 31, then that means that z would have to be equal to 53 for the terminal digit to match up. If x is equal to 17 and y is equal to 37, what's the terminal digit there? It's 9. So the terminal digit of z would have to be something ending in 9. 49 is close to 51, but it's not a prime number. 59 is a prime number, as far as I can remember, but I think it's a bit far away. So, okay, I'm going to put it down as a possibility just for now. But I think that the combination that we're looking for is probably going to be this: x equals 17, y equals 31, z equals 53. How do I know? Well, I've got to check. That's the only thing that I can do. So let's find what the product of 17, 31, and 53 is. And now I do need to calculate precisely. So 17 times 31. 17 times 3 is 510 plus 17, so that's going to be 527. So 527 times 53. 527 times 5 times 100 is going to be 52,700. So times 50 is going to be 26,000. Is this right? 350. 26,350 plus 3 times this, which is going to be 1,581, which is 27,931. Is that right? Yeah, there we go. So x is equal to 17, y is equal to 31, z is equal to 53 is the solution to our problem.